Welcome to Calculus. Today we will investigate applying derivatives of products and quotients to scenarios. And in specific, we'll be looking at a free fall scenario, focusing on using the definition of the derivative and the rules that we've developed as shortcuts to solve real life, in this case, free fall problems. So we've got one scenario here that has a number of parts, so A through G. Let's take a look at the situation. So a ball is thrown vertically upward from a height of 6 feet. So a person standing at 6 feet above the ground throwing a ball vertically upward with an initial velocity of 80 feet per second. The distance s in feet of the ball from the ground after t seconds is this function, s of t equals 6 plus 80t minus 16t squared. So we'll start in with our questions. Our first part here is really asking about the derivative. It says, what is the velocity of the ball after 2 seconds? So what we need to do is, first of all, figure out how can I represent the velocity of the object in terms of an equation. Well, recall from physics that our position function, we could consider that our original. The derivative of the position function would give us the velocity function. So if my position function in this case is the s of t, our velocity function, which we could call v of t, is equal to the derivative of the position function. And that's where we need to begin with our calculations. So I'm going to bring s of t, just record it again here, and then we'll take its derivative, and then we'll find out what's the velocity after 2 seconds. So again, the original is 6 plus 80 times time minus 16 times time squared. So the derivative of this one is going to be my velocity function. Again, just saying where it comes from, it's the derivative of the position function. So we're going to differentiate in pieces. So the derivative of the constant 6 is 0. And then applying my constant coefficient rule, 80t, I let the 80 stay in place. And then the derivative of the linear t is just 1. And again, the constant coefficient rule, I'll let negative 16 stay in place, and then apply the simple power rule, bring down the old power of 2 as a coefficient, times time to the power of 2 less 1. So we just need to simplify, and what that gives us is this much simpler linear function. 80 minus 16 times 2 is going to give us 32 t to the power of 1. And that's my velocity function. So that's a good one to kind of circle. It's not our answer here, but we'll use it again. So we'll circle it to let it stand out. Now we need to find the velocity of the ball after 2 seconds. So really we're calculating the velocity at 2. So I'm going to put the 2 there for the x, and let's substitute it in for any occurrence of t. So 80 minus 32 times parentheses 2, and that's pretty quick to calculate. That's 80 minus 64, and that's going to give us a velocity of 16. And we can put our units here. I notice the initial velocity from the questions in feet per second, so we'll stick with feet per second, 16 feet per second. So just thinking about how the course of this object, this ball being thrown upward, would go, it would go quickly from the hand, and then as it went up, slow down because of gravity. And that's why we're seeing our velocity after just 2 seconds has decreased from 80 down to 16. Well, let's look at part B. Part B is really asking, well, when's it going to reach its maximum height? So there's different ways to find that value. If we consider the position function, which is a quadratic, it's really where the vertex is located. So just to kind of sketch in a graph here, it's starting from a height of 6 feet, and the function's quadratic and it's opening downward because of the negative coefficient. And this point at the very vertex right there, that is going to be my time to reach the maximum height of the flight. And then if I wanted to know the maximum height, that's the y value there, f at t, of the vertex. And that's actually part C there. So let's bring our function back. So just again, s of t equals 6 plus 80t minus 16t squared. So recall from Algebra 2 and Algebra 1, to find the x value of the vertex of a quadratic, we'll put t of the vertex is given by this small term negative b divided by 2a. So to do that, I just need to identify in my equation for the position, what's my a, my b, my c. So I do want to rewrite it so that's in standard form. So negative 16t squared, you put the quadratic first, plus 80t plus 6. My first coefficient is a, second is b, third is c. So for our vertex here, what we want to fill in is negative, my b term's 80, so negative parentheses 80 over 2 times, and then my a term is negative 16. And that I just want to simplify. So I see the negative signs there are going to cancel out, so that's good. The time will be positive. And then I've got 80 over 32. I can divide 16 of those out. That would leave me with 5. If I divide 80 by 16, it equals 5. And that would leave 2 in my denominator divided by 16. So then I've got 5 divided by 2, which is going to be 2.5. And since that's time, seconds, 2.5 seconds. So then that brings the next question, what's the maximum height? So again, we've already anticipated that maximum height, I'll just highlight it here in green, is the y value when I plug in 2.5 into the position function. So we can do that. So we'll zoom down here to part C. What's the maximum height the ball reaches? So again, I'm going to put s of t. We'll put it in standard form. So we had just inverted the order. Negative 16t squared plus 80t plus 6. And what we're really interested in is what is the position after 2.5 seconds. So s at 2.5. So we'll just plug in here into the function. So it's negative 16 times 2.5 squared plus 80 times 2.5, and then plus 6. So let's calculate that out. 2.5 times 2.5 from that squaring is going to give us 25 times 25 is 625, 2 decimals, so 6.25 times 16. So again, I'm just taking care of that first term here. Let's highlight it. That's what we're looking at right now. So we'll multiply times 16, so that's 30. 12 is 15, and that's 37. And then 625, add it all up. And carry my 2 zeros. That looks like we got 100 there. And that's actually going to be negative. So that's negative 100. And then let's add the next term. So again, now we're looking at 80 times 2.5. So we'll multiply that out. We'll put the 2.5 first since I got that 0 in the 80. So 0, and then 8 times 5 is 40. 8 times 2 is 16, 200. So it's negative 100 plus 200 plus 6. And when we add that all up, 200 minus 100 is 100. 100 plus 6 is 106 feet. So that's the height of the ball. So it's gone quite a distance, 106 feet into the air, and in a matter of 2.5 seconds. So that takes care of that initial stuff. That's it uses calculus in order to find the velocity function. And then we kind of use some algebra in parts B and C. Part D, we return to calculus. What's the acceleration of the ball at any time? So what we should establish is, how do I get there? So just to make this connection again, if I've got a position function s of t, its derivative, as we've already seen, is going to be velocity. So we'll say the derivative of s of t is velocity. But then if I took the second derivative of my position function, so I'll notate that as s double prime of t, which really is the first derivative of my velocity function, that would equal acceleration. So we can look at it in a couple different ways. It is the double derivative or the second derivative of the position. It's also the single or the first derivative of the velocity, and that's how we're going to calculate it. So just to bring back velocity here, we had calculated that that has the equation of 80 minus 32 times time. So let's calculate the derivative. So the derivative of the velocity function, which we're going to interpret as the acceleration function, is, so derivative of 80, that's a constant, is 0. Derivative of negative 32t, negative 32 stays put as a coefficient, and then the derivative of the linear t is 1. So that's very simple. The acceleration function is going to be simply negative 32. And from a physics standpoint, that makes sense. That is the acceleration due to gravity. So we could even put our units, that's the feet units, feet per second squared. And that is the acceleration of the ball at any time t, again, because of the physical constraint of gravity. Part E then turns back to some algebra. It says, how long is the ball in the air? So we need to just interpret that in terms of our function. So I'm just going to sketch it again. We had said, okay, this is a rough graph. It starts from 6, it's a quadratic, and then it at some point goes back to 0. So this interval of time is the length of time that the ball is in the air, because that's from the moment it was released upward at a height of 6 feet, went up, reached a velocity of 0, and then fell back down to the earth past the 6 feet, actually hitting the ground. That's our time. So in terms of solving, we need to say, okay, when is the height of the ball 0? Because right here, this point here would be t comma 0, because that's an x-intercept. So to do that, again, I'm going to take the position function. So let's bring that back, s of t, and I'm going to write it in the standard form. So negative 16t squared plus 80 times time plus the 6 feet that we had started from. So if I think, okay, what's the position when the ball hits the ground? Well, that has to be that y value of 0. So really what I'm doing for part E here, it's an algebra 1, algebra 2 question, solving a quadratic. Many different ways to solve a quadratic. Since we've got it in standard form, let's set it up for the quadratic formula. So a, b, and C. My A is negative 16. My B is positive 80. My C is positive 6. So to bring back the quadratic formula, it starts by saying the domain value. So T equals, it's a big fraction, negative B plus or minus the square root of B squared minus 4 times A times C all over 2A. And we'll just fill in right here. So my B values, there's 2 of them. So I'm going to take those out, and instead of those, I'm going to put 80. Now I'm very careful always to use parentheses. Not so critical when the B value is positive. We do need them when it's negative. So again, there's 2 places where I would substitute A, which in this case is negative 16. So I'm going to put definitely parentheses around this negative value. And then one last place where we would input the value of C. C has the value here of 6. Now we just need to solve that. So what I'm going to do is I'm going to head over to Desmos and calculate it on the calculator, because it could be that it's an irrational number. Let's go see. So here's Desmos. We got our function already graphed here. And you can kind of see Desmos gives a nice shortcut. You can actually just click on that 0, and it tells us it should be 5.074 seconds. Let's see if our quadratic formula gives us that answer. It should. So I'm going to type in negative parentheses 80 parentheses. When we get to plus or minus, we choose. So I'm going to put plus first. The square root of 80 squared minus 4 times, in parentheses, negative 16, close the parentheses, times 6, all over 2 times my A term, which again is negative 16. So that's obviously giving us the left 0. I can find it here on the graph. It's about negative 0.074. Does that make sense in terms of a time value? Can I have negative time? Not unless I'm traveling to the past. So I need to go back into my quadratic formula and change plus to minus. Remember, there's 2 solutions. And that gives me my 5.074 that I saw on my graph. So that works. We'll head back to our notes, 5.074, to finalize that question. So that gives me, again, 2 solutions, but we choose the positive one. Time is about 5.074 seconds. That'll box it, because that's the answer there. So again, that's just an Algebra 1, Algebra 2 question thrown in the mix with the calculus here. So then the question for part F says, what's the velocity upon impact with the ground? What is its speed? So if we think, we wrote a velocity function, so let's bring that back. Velocity, remember, it was the derivative of the position. So we had written that as 80 plus, in fact, we'll just write it as minus 32 times time. So if we're interested in the velocity of the ball upon impact with the ground, we're really saying, what's the velocity at 5.074 seconds? And we'll put that just to show we're substituting in the red, 5.074 equals 80 minus 32 times that 5.074. And that we can substitute back in, probably get that most quickly calculated on Desmos. So I'm going to write it down, and we'll just crunch that number real quick since there's so many decimals. So let's calculate we'll call this, well, we don't have to give a function because we're just evaluating. So 80 minus 32 times 5.074. And it looks like our velocity there is negative 82.368. And we'll record that here. So the velocity is about negative 82.368 feet per second. So then there's a question. I'm going to go ahead and box it because that's one of the questions. What is the velocity when it hits the ground? What is its speed? So we just have to ask kind of the difference between speed and velocity. And that's really a physics question. They're the same thing with the difference that the velocity includes a direction. So notice that our velocity turned out to be negative because really our motion for this object, this ball, is upward, away from the earth. We're throwing it up away from the earth. The direction that it's moving when it returns to the earth is opposite that original direction. So that's why it's got this negative value. But in terms of speed, what we would say is, hey, the speed is just what's the magnitude of that velocity? All we got to do is take off the negative. It's 82.368 feet per second. So again, that's just a physics consideration to say the velocity, which we would say is a vector, has both magnitude and direction. Whereas speed, it's not a vector, we call it a scalar, has only magnitude. So it wouldn't tell me which direction the velocity or the rate of this object, how it's changing. Okay, so let's take a look. Let me write that last part so I get it recorded. So speed is a scalar, and that is everything but the direction. It's the magnitude. Okay, so got that there. Let's take a look at our very last question here. So part G, what is the total distance traveled by the ball? So we just have to think about our position function, because whenever you see distance, that's really the position. So let's just consider our graph again. So again, it started from a height of 6 feet, went up, reached a maximum, and then went back down. So we had already calculated this height of the ball to be 106 from the ground to the vertex. So really there's two parts to this journey of the ball flying into the air. It really flies up into the air, reaches a zero velocity because of gravity slowing it down, and then succumbs to gravity and starts falling all the way back down to the ground. So those really are just two separate paths. So from the first path, if we're starting from 6 feet and it goes to a height of 106 feet above the ground, that first travel upward would have gone 106 minus 6, which would give us a journey of 100 feet into the air. Let's put an arrow on it because that's headed up. The return trip, so from the vertex back to the ground, would be the full 106. So all we got to do is say, okay, if there was 100 feet traveled upward and then 106 feet traveled downward, that's going to give us a total of 206 feet. Well, thank you for joining for this consideration of applying derivatives and second derivatives to a real life situation here, a free fall of a ball thrown up into the air and then coming back to the ground. So I'll let you go work on your own first and second derivative applications. See you soon.